volume optimization of origami bellows for space habitats. In this research, we examined the potential application of origami bellows for space habitats. And this is one of most commonly seen origami structure, the mural sheet, which this is rigid foldable one, which means when you compress it along X or Y axis, the facets will not deform. And origami can also be folded into cylindrical structures like the Kreslin pattern, this one. And it is non-rigid foldable, which means when you compress it, the facets will deform. And this will lead to the multi-stability. We can see from the strain and the potential energy plot that there are 3 local minimum, which are the 3 stable states of the Kreslin. And the change of the potential energy are due to the deformation of the facets. And this is a conventional space habitat. It cannot be folded or deployed. And these 2 are origami-based space habitats. It can be stored into a compact configuration for launch. And they can also be deployed once in the orbit. And this is the deployment procedure of a mural array-based space habitat. We can observe the volume expansion here. And so the motivation of the origami space habitat is to improve the volume expansion ratio. And this is the geometry of the tri-stable Kreslin. Normally, the Kreslin is folded along the long diagonal like this one. And it might have 2 stable states, this one and this one. And if we twist it a little bit, it will the facet will pop out along the short diagonal. So we here introduce another crease along the short diagonal, which is the crease pattern 2. And it could also be stable at this state. So these are the 3 stable states of the Kreslin pattern. And we have also proved that for Kreslin, if it can be stable when folding along crease pattern 1, then it can also be stable when folding along crease pattern 2. And the structure can be described by sector angles phi1, phi2, the radius r, the number of unit cells of each layer n, and the number of layers m. And the right figure is the volume change during the deployment from S1 state to S3 state for the whole design space of phi1 and phi2. And all the colored areas are the feasible design space. And this is the volume ratio of the volume at S3 state over S1 state. We can observe that all the ratio is greater than 1, which means the volume is increasing during the deployment, which makes it possible to use inflation of the evacuation method. And we choose SpaceX Falcon 9 as the transporting rocket, so its payload fairing provides the upper limits for the stored volume. And our objective is to maximize the volume deployment ratio, and we describe it by effective deployed volume over the volume of the fairing. And we choose particle swarm optimization under several geometric and manufacturing constraints to optimize the design parameters. And the result shows that the tri-stable Kreslin can provide a volume deployment ratio of over 2.5. And at the same time, the cross-section area remains the same, which is beneficial for the design and manufacturing of the bulkheads that attach to the top and the bottom of the bellows to make it airtight. So to conclude, our research showed that origami bellows have high potential energy for space habitats because the internal volume is increasing during the deployment, and the multi-stable origami bellows offers significant volume increasing ratio. And as for future work, we will include structural analysis and consider the manufacturing details. Thanks for listening. Welcome any questions.